So in this last video, hopefully it's the last video, maybe one more with examples, but in this video, we're going to look at some problems, some questions that are related to kinetic potential energy and how the two interplay with each other. So in this first one, we have a roller coaster, and we have 2 points marked on the roller coaster. Point 1 is up here at the top of this hill, and point 2 is down here at the bottom of this little valley. All right. So we want to know which statement correctly compares the kinetic energy and the potential energy at points 1 and 2. So we're looking for things like which point has the highest kinetic energy or the lowest kinetic energy, and which point has the lowest potential energy or the highest potential energy. All right, so if we look at our options, first option says kinetic energy is highest at point 1. So it's up here. Is this the highest kinetic energy? All right. And it's lowest at point 1 and highest at point 2 for potential energy. Okay, well, kinetic energy is not highest at the top. So we need to go down to the next one. Is kinetic energy highest at point 2 down here in the trough? And is potential energy lowest at point 2 while highest at point 1? All right, and then the next two options, both kinetic and potential energy are highest at point 1 and lowest at point 2, or they're both highest at point 2 and lowest at point 1. So we already know that as kinetic energy goes up, potential energy has to go down. So options C and D do not work. All right, now the question is, does the potential energy or kinetic energy max out at the top of the hill? All right, well, potential energy is going to be highest at the top of the hill, which means kinetic energy is going to be the lowest, which means at the bottom of the hill, kinetic energy goes up, potential energy goes down. So the correct option here would be B. All right, so now we have this diver standing on the top of the platform. We know the mass of the diver, we know the height of the platform. First question is to calculate the potential energy. So we're going to take 70 kilograms, multiply it by 3, multiply it by 9.8. All right, that's going to give you the potential energy. Now, the potential energy has to equal the kinetic energy. The kinetic energy has to equal the potential energy because we don't have friction, which means whatever we get, 70 times 3 times 9.8, that's going to be our kinetic energy for the fall that the diver moves through. All right, so we do that. 70 times 3 times 9.8 gives us 2,058 joules. That's the same as the kinetic energy. Now we're going to use the kinetic energy equation to solve for the velocity. So we're going to take this energy, we're going to multiply it by 2, then divide by the mass, which is 70, then take the square root of that. So the speed will be 7.7 meters per second. Now, I'm happy to work this out with y'all in class. I just don't think I'm going to be able to do it on this video, but we'll work through this in class, and if I need to do some more videos with these types of problems, I'll be happy to do that. All right, same thing with this one. We want to draw a double curve line graph showing the changes from potential energy to kinetic energy. So we want energy on our y, the process or the time of the swing on our x. And we're going to track the changes in energy. We have one line for potential energy where the potential energy would start high and then would go low, and then as it swings back the other side, it's going to go, potential energy is going to go back up, but our kinetic energy will be drawn with a second line, which is going to start low because it has 0 kinetic energy to start. Then as the potential energy goes down, the kinetic energy goes up, so that when potential energy 0, kinetic energy is maximum, and then it's going to go back down again. Again, I'll draw this in class as well. All right, I believe this is the last slide. All right, now in this particular image, we've got the path of a student on a sled. They're starting from rest at point W, and they're going to slide down this snow-covered hill. It's frictionless, so we don't have to worry about efficiency, and they're going to pass point Z. All right, now Z is at the ground level, but they're going to continue past because they still have forward momentum. So which of the following statements best describes the energy of the student and the sled from point W to point Z? All right. So A, is the total energy at point W less than the total energy at point Z? Or B, is it greater? So does this have a greater total energy than this? Or C, the potential energy at W becomes all kinetic energy at Z? Or the reverse? Does the kinetic energy at W become all potential energy at Z? So take a second and think about that. Which one could it be? Now, hopefully you eliminate choices A and B, because choice A and B says that the total energy at one point is greater than the total energy at another point. Since we have a frictionless situation, there's no loss of energy to heat, so there's no dissipation of our usable energy. So our total energy should be the same at point W and point Z. The difference is going to be which one is kinetic and which one is potential. It's going to be in all one form or all the other. And we need to figure out which form it's in at which point. So when we're on a slope like up here at point W, we have all potential energy, and then that potential energy is going to become kinetic as we fall that distance from W to Z. So the answer here is C. The potential energy at point W becomes all kinetic energy at point Z. All right, so that's it for the slides. Let's look at this calculation in a little more depth. Once I get my tablet hooked back up, and we can work through the problem. All right, so we have this. Oh, I unplugged my mouse to do this so I can use the tablet. All right, so we have a diver, and the diver is starting up here on the diving board, right? That's a terrible diving board. All right, so we have our diver up here. Do we know the mass of the diver? So I know that the diver has 70 kilograms of mass, so I'm going to write that over here. Mass is 70 kilograms. And then I also know that the platform is 3 meters. So I know that this distance here is 3 meters. So my height is 3 meters. And I know that the gravitational acceleration is 9.8 meters per second squared. So the first question asks, what is the gravitational potential energy? So gravitational potential energy is mass times the gravitational acceleration times height, which in this case is going to be 70 times 9.8 times 3. And that's going to give us, I had it, 70 times 9.8 times 3. It's going to give us 2,058 joules. All right, so that's the answer to the first question. The second question is, how fast is this diver falling? What is this diver's speed right before they hit the water? So we know that in this case, the potential energy is going to equal the kinetic energy. So I'm going to use this 2,058 joules as my kinetic energy. We also know that kinetic energy is equal to 1/2 mv squared. So I'm going to rearrange this and solve for v, which I did in the last video. So the velocity is going to equal 2 times our kinetic energy divided by our mass. We're going to take the square root of that to get velocity. So square root of 2 times 2058 divided by 70. Right, remember this is units of joules and units of kilograms. So taking that kinetic energy, multiplying it by 2, dividing it by 70, and then taking the square root gives me about 7.7 meters per second. All right, so 7.7 meters per second would be the velocity of the diver right before they hit the water. All right, in the next slide, it talked about drawing this double curve line graph showing the changes in potential energy as the bowling ball swings from one side to the other, back and forth. So here's our picture of what this looks like. So I've got my bowling ball here. It's going to swing this way until it's over here, and then it's going to oscillate between those, move back and forth between those two positions. So we're going to draw our graph where we've got the position here. All right, it's our x coordinate, or the time. So our time of the swing. We could also look at this as the angle that this is moving through. And then we're going to put our energy here. Now we have our potential energy at this angle here, this position, this time of the swing before we let it go. Our potential energy is going to be maxed out. All right. And that potential energy is going to decrease as it goes through the swing until it hits the bottom of the swing right here, that midpoint. And then it's going to go back up until it reaches that same level. So this line here would be our total energy. This green line is our potential energy. All right, now our kinetic energy starts off at 0 because it's not moving yet. Right, so here, kinetic energy is nothing, there's no speed. It's going to go increase until it hits this line, until all of our potential energy has been converted into kinetic energy, and then it's going to decrease until it hits this point again. All right, my line is not drawn right. All right, so this pink line would be our kinetic energy. All right, so notice that at some point our potential energy line crosses our kinetic energy line, because that's when half of our energy is kinetic and half of our energy is potential. All right, so that's it for this lesson of videos. I'm sorry some of them are kind of on the long side, but it just was how things went. All right. If y'all have questions or we need to go over any of these examples or different examples, we can certainly do that in class. All right.